revision of concept of eigenvalues and eigenvectors. Then look at the concept of a multivariate function and how you'll define the derivatives of a multivariate function, that is first derivative and second derivatives. Then we'll look at use these concepts to define optimization, to find out how to optimize a function, a nonlinear function, and also how to do constraint optimization using the method of Lagrangian multipliers, because we'll need to use it in a couple of places later on in the course. Then we'll look at how to solve a system of linear equations, right? Because the solution of a lot of problems is ultimately translated into solution of a set of linear equations. So I think that's about it, and after that we'll start with our get back to our data. So let's start with vector spaces. So as you know, there are certain conditions, right, which vector spaces satisfy. There are a couple of rules. So if U and V are vectors, right, which are elements of this set called a vector space, which is denoted by capital V, then the addition rule says that sum of U and V, so there is a summation operation that is defined over these vectors, right, and U plus V is also in V, in this uppercase V. Then there's a multiplication rule where you can define multiplication of a scalar A is a real number, with the vector U. So V is in the vector space V, so U is in the vector space capital V. Then if it is multiplied by a scalar A, then A times U is also an element of the same vector space V. Then we also define a zero vector. So you can write it as simply bold zero, or sometimes in some notations people use like a zero with a slash, across it. So you can use whatever, either of them. So we have define a zero vector, with a capital zero. Then A dot U is 0 if A is 0, right, and A dot U is 0, there is a zero vector if U is a zero vector. So if you multiply zero vector with any scalar, you get the zero vector, right? If you multiply any vector by the scalar 0, again you get the zero vector. So that's what it says. So you basically have the addition rule, multiplication rule, and a couple of operations related to the zero vector. Then once you have defined a vector space, then we can define the concept of linear combination. Since we have defined two operations, summation of vectors and multiplication of vectors by scalars. The generalization of that is a linear combination. So you can take the sum of this kind of scalar multiples of vectors. So that is sigma ai ui, right? That's a linear combination of right, of a bunch of vectors where all the u's come from a vector space capital V, and all the a's, the coefficients, are real numbers. Now, once you define a linear combination, you can define the concept of linear independence. So let us assume that for certain values of A and certain vectors ui, so as you can see here, okay, let us assume that the linear combination is equal to 0, as you can see here, right? And there's a little printing problem here, typing problem. So let this equation be true, right? So insert that here, such that not all AI is 0. Then we say that UI are linearly dependent. That is the only way you can sum a bunch of, or take linear sum of a bunch of vectors and produce zero vector, is when the vectors are linearly dependent. That's basically the idea. Now, you know all these concepts from your high school, I guess, but I just want to quickly revise it. So otherwise, UI are linearly independent. So that means the vectors U1, U2, etc. are linearly independent only if the linear combination of them when it is equal to 0, has only one trivial solution. That is, the only way you can produce 0 by taking linear sum is by having all the coefficients equal to 0, each of them, by having them equal to 0. Then you say that the vectors are linearly independent. So once you define linear independence, you have the concept of rank, right? So matrix is, you can think of it as a bunch of columns or a bunch of rows, right? And so let's say A is a m by n matrix, and it's denoted by this notation. Then the rank is defined as min of the linearly independent rows or columns. So you have this. Then inner product and outer product. So if you have two column vectors, so one thing is, if one convention will follow in this entire course is, a vector is always, when you denote a vector as a matrix, right? That means it will be either it can be either a row matrix or a column matrix, but we'll always denote it by a column matrix, just as a convention. Do some kind of n by 1 kind of a matrix. So if two vectors, which are column vectors, right, with the same size as, they have the same size, then U transpose V is inner product. So inner product, you know, right? If you have two vectors, so with components UI times VI, okay, that's the inner product. This is what you denote by, right, this dot, big dot. Now the same operation in matrix notation can be described like this: U dot P is equal to U transpose of P, because U transpose gives you this, and this gives you a scalar. There's a different kind of product that you can also define between vectors, again between column vectors. That is called the outer product, and which we'll also be using in this course a few times. So outer product is, inner product is U transpose V, outer product is U V transpose. So since we always assume that the vectors are always column vectors, U V transpose will give you a matrix, whereas U transpose V gives you a scalar. It's a reduction of dimension, whereas here this expansion of dimension, you get a square matrix. So like this, right? So for example, if you have a vector U as, like, say 1, 2, 3, and let's say V is also the same. Okay, so U transpose V is 1 square plus 2 square plus 3 square, so which is a scalar. Whereas V transpose U, change the color here. So V transpose U will be 1 times 1, 1 times 2, 1 times 3, 2 times 1, 2 times 2, 2 times 3, and 3 times 1, 3 times 2, 3 times 3. Okay, so that's your outer product matrix. So now let us come to, so we have defined the vector spaces and two kinds of products of vectors. So then let us look at eigenvalues and eigenvectors. We'll start with square matrix, but later on in the course we'll mainly stick with square symmetric matrices. Okay, so let's start with square matrices. So for a general square matrix, the eigenvalues and eigenvectors are defined by this eigenvalue equation given by Ax equal to lambda x. So that is, what is a vector when you multiply A and X? You simply get the result will still be just a scalar multiple of the same vector. That is, you don't rotate, there's no rotation of the vector, there's only kind of stretching or shrinking. Right? What is the direction in which this operation, when you multiply with the matrix, right, you get this kind of a result. So this you can modify, you can bring this lambda x to the left side, right, and you get Ax minus lambda x equal to 0. So that's a 0 vector, and so that means the determinant so that's a 0 matrix. So the determinant of this must be equal to 0. So so determinant of A minus lambda I equal to 0. This will give you a polynomial equation in lambda. So if it is an n by n matrix, you get a nth order polynomial equation in lambda, and when you solve that, you get n complex roots. In general, they are complex, but you can also have real numbers. Right, and these are the eigenvalues, and the correspond. And if you plug this back in this equation, you get the corresponding eigenvectors. So it's can be a bit tricky, but let us look at a small example. Eigenvalue calculation is straightforward. Eigenvector calculation can be a bit tricky. So let us look at a small example. So A is given is a 2 by 2 matrix given by 1, 1, 4, and minus 2. So if you solve this, so A minus lambda I mod is equal to 0. So that is 1 minus lambda 1 4 minus 2 minus lambda, right, is equal to 0. So 1 minus lambda times 2 plus lambda minus 4 equal to 0. So you get basically 2 and minus 3 as a root. Now, how do you get so these are the eigenvectors, but how do you get them? So let us plug it back in the equation. So Ax is equal to lambda x. So that means A minus lambda I, right, times x is equal to 0. So we need to solve this and find x. So 1 4 2 minus 1 4 1 minus 2, right, minus lambda 0 0. So this whole thing times x equal to 0. Okay. So if you take lambda is equal to 2, right, you get 1 minus 2, that is minus 1, 1, 4, and minus 2, that's minus 4. Right. This times, let's say x1, x2 is equal to 0. So you can see that both equations are the same, right? So you can get whole. So you can have solutions over an entire line, right? So let us see that. So the answer will be x is 1. So let's say x1 is equal to 1 and x2 is equal to minus 1. So that should do. Oh, sorry. X1 and x2 are both 1. So that is this thing. So it can be any multiple of this. So people generally take a normed, vector. So you can have x1, x2 is equal to 1, 1 by root 2. Okay, so you can do that. You can do the same operation and get the second one also. But the problem is finding eigenvalues is straightforward because when you expand this determinant, you get a nth degree polynomial, and if you solve it, you get n roots. Because right, the fundamental theorem of algebra says that if you have nth degree polynomial, you will always have n roots. They can be real or complex. You may not be able to solve it analytically, but you always have n roots. But you may not have distinct solutions for the eigenvector problem. Okay, even though you have this eigenvalues may or may not be distinct, but the eigenvectors may not exist. Distinct eigenvectors may not exist in all cases. So let us look at a small example for that. So a matrix where you don't have n eigenvectors. So it has always n eigenvalues, but if it doesn't have n eigenvectors, then such a matrix is called a defective matrix. An example of that is this. So let us see this. Why it doesn't have n eigenvectors. So it is a 2 by 2 matrix of a general form. This is only an example. Okay, not that no other matrix is defective. So A, B, 0, A. So this is the matrix. So if you solve for eigenvalues, you have A minus lambda, B, 0, A minus lambda is equal to 0. So A minus lambda whole square is equal to 0. So lambda is equal to A. Okay, basically it's a it has two eigenvalues, both are equal to A. So then you say that this eigenvalue A lambda is equal to A has a multiplicity m equal to 2. That is the same eigenvalue occurs many times. Right here, that's called multiplicity, and it occurs. It is 2 for this number. Now, how do you get the corresponding eigenvector? So you plug this lambda back into the equation and solve for it. So the equation now becomes A minus A, B 0, and A minus A. So this times x1, x2, this is equal to 0. This is what we need to solve. So which looks quite crazy because it is 0, b, 0, 0. All right. Okay, so the first part basically says x2 b is equal to 0. I assume b is non-zero. So x2 has to be 0. For the second equation, 0 times x1, 0 times x times plus 0 times x2 equal to 0, that is useless, right? You can't do anything with it. From the first equation, it says you have x2 equal to 0, and x2 can be anything. Sorry, x1 can be anything. So you can take the norm case and have the vector as x1, x2 is equal to 1, 0. Okay, so that gives you one eigenvector, but what about the other one? So there's only one eigenvector. So there are two eigenvalues of multiplicity 2, and the values are a and a, but there's only one eigenvector. There are cases where, for example, in a symmetric matrix, you always find n eigenvalues and also n eigenvectors. But for a general matrix, it is a non-symmetric matrix, you will always have n eigenvalues, but you may not have an eigenvectors. When you don't have the full set of eigenvectors, such a matrix is called a defective matrix. That is only a small example. In the course, we'll be dealing with mostly symmetric matrices. And for a symmetric matrix, there's no problem. You'll always have n eigenvalues and n eigenvectors. Right? And not only that, they'll all be found orthonormal set. So life is pretty clean and simple. So let's look at some properties of the symmetric matrices. So a matrix is called a symmetric matrix if A transpose is equal to A. So you know this. That is when Aij is equal to Aji. And it is called a Hermitian. There's a more general case where if the elements of the matrix are complex, so if it's a complex matrix, right? That is A is inside the complex matrix. Okay, so then that's called a Hermitian. And then again, symmetric means it's not only Aij is equal to Aj, but Aij is equal to Aj star, the conjugate. So star denotes the conjugate. So for a real matrix, there's no problem. You don't have to mention this, but for a complex matrix, you need to mention that when you flip the matrix, you need to also conjugate the elements. Okay, and so that which means that the diagonal elements should all be real because they won't change. Right? So then there is a different kind of matrix called a skew symmetric matrix, for which A transpose is equal to minus A. That is the diagonally opposite elements will have opposite signs, right? And so basically you can see the notation here is if it is a Hermitian, then we use the notation star, right? If it is a real matrix, we use the notation T in the uppercase. But let us just stick with T and assume that if it is a complex matrix, we'll make sure we do the conjugation. Okay, we won't be dealing with complex matrices in this course, but I just want to mention that this is the general notation. Okay, so if it is real, you call it skew symmetric matrix, and if for the corresponding complex case, you call it skew Hermitian. Okay, so that is this. Now, the eigenvalues are very clean for a Hermitian matrix and the skew Hermitian matrix. The Hermitian is a general case, right? So when I say Hermitian, it also includes the real symmetric matrices. So the eigenvalues of Hermitian matrix are all real, and why is that? It's easy to show. Let's take the eigenvalue equation Ax equal to lambda x, then multiply both sides by x transpose. You get x transpose Ax is equal to lambda into x transpose x, and x transpose x is this mod x square. So this is a norm notation. is norm, and so we'll assume L2 norm. So that means L2 norm is equal to sigma mod xi square power half. Okay. So x transpose x equal to lambda mod x norm x squared. Then take transpose of both sides, right? Trans on both sides, right? So you get x transpose A transpose x on the left side. On the right side, transpose of lambda will be its conjugate, right? We have just seen that. So lambda star, and this is scalar, so transpose doesn't affect it. It will still be norm x squared. Now we know that since A transpose is equal to A, we get x transpose Ax is equal to this. Okay, so left side is same here. So this and this are the same. Therefore, lambda norm x square is equal to lambda star norm x square. So therefore, lambda is real. So norm lambda is equal to lambda star. So lambda is real. So all the eigenvalues of a Hermitian matrix are real. Now, similarly, if we take a skew symmetric or a skew Hermitian matrix, right, they are all purely imaginary. And why is that? Because of the small difference. In the previous case, A equal to A transpose. In this case, A equal to minus A transpose, and that makes a difference. So again, multiply both sides by x transpose x is equal to lambda x transpose x. Then x transpose x equal to lambda norm x square, right? And then transpose both sides. So trans both sides. Okay, you get x transpose A transpose x, and this is actually this should be star. And so A transpose becomes minus A, so you get minus x transpose A x equal to this. Okay, so you have, so if you look at this equation, you get lambda x mod x norm x square is equal to minus lambda star norm x square. So lambda is equal to minus lambda star, so that which means that lambda has to be purely imaginary. So this is straightforward. Now we'll define a matrix called an orthogonal matrix, and we'll see that because an orthogonal matrix and a square matrix are closely related. Right. So let us define orthogonal matrix. It is a matrix Q, it's a square matrix Q, such that Q transpose Q is equal to Q transpose equal to I. That means so Q transpose is equal to I. Okay, so basically what that means is like Q transpose is equal to Q inverse. Okay, because only when you multiply two matrices, matrix and is inverse, you get the identity matrix I. So therefore, when you do transpose, you get the inverse. So that is the orthogonal matrix. For such a matrix, all the eigenvalues are of unit length. Okay, so that means they sit on the unit circle in the complex plane. Why is that? So let us start with the eigenvalue equation again. Qx is equal to lambda x, and so then take the transpose. Okay, x transpose Q transpose is equal to lambda star x transpose. And then multiply. So I'll call this equation 1, call this equation 2, multiply 1 and 2. So you get this. Now you know that Q transpose Q is equal to I. So you get x transpose x here. And here you get lambda star x transpose x. So x transpose x is norm x square is equal to lambda mod lambda. So this should be square here. Norm x square. So mod lambda square is equal to 1. So that means lambda has to be right of the form e power ij. Or e power I theta, sorry. So what, to summarize these three results, if you look at theorem 1, okay, for a symmetric matrix, all the eigenvalues, okay, I'll put all them together in this picture. So eigenvalues are on the real axis. So this is the real axis. This is the imaginary axis. So eigenvalues are on the real axis for a symmetric matrix. Eigenvalues are on the imaginary axis for a skew symmetric or a skew Hermitian matrix. And eigenvalues are on the unit circle. Oops. Okay, for a orthogonal. So that's how the three eigenvalues are related. But yeah, so now let us look at how an orthogonal matrix is related to a symmetric matrix, because we'll be using these concepts. I'm trying to give the minimal set of uh, principles or properties or mathematical tools necessary in this course. So linear algebra itself is a huge, it's an ocean, right? I mean, you have most of done courses in your first year or maybe second semester. But I'm just giving the bare minimum needed to get through in this course. So the eigenvectors of distinct eigenvalues of a symmetric real matrix are orthogonal. Okay, so and therefore the eigenvectors of a symmetric matrix can be used to form an orthogonal system, and you can use a set of such eigenvectors to construct an orthogonal matrix. So we'll see that in a minute, right? So why are the eigenvectors? So in general, eigenvectors of a matrix, of a square matrix, need not form an orthogonal system. That is assured only for a symmetric matrix. So let us take real symmetric matrix, and let us say U1 and U2 are two eigenvectors, and lambda 1, lambda 2 are the corresponding eigenvalues. And we'll also assume that they are non-zero vectors in Rn. Now take the first equation, A U1 is equal to lambda 1 U1, and pre-multiply this by U2 transpose. So you get, since that you get lambda, take this lambda 1 out, like lambda 1 times U2 transpose times U1. Okay, that is equal to U2 transpose. So you can, so it will be U2 transpose times lambda 1 U1. Now, lambda 1 U1 is nothing but AU1, that is from the first equation. So you use that here. And now in this expression, just rearrange terms a little bit, regroup terms a little bit. So you take U2 transpose times A multiplied by U1. Now U2 transpose times A can be written as A transpose U2 and transpose of the whole thing, right? Times U1. Now A transpose is same as A because A is symmetric. So therefore you get AU2 transpose of the whole thing times U1. Now AU2 is nothing but lambda to U2. So we'll plug it in here. So you get lambda to U2, right, transpose of the whole thing times U1. Okay, so that is what you get. So therefore, you find that lambda 1 U2 transpose U1 is equal to lambda 2 U2 transpose U1. So which means lambda 1 minus lambda 2 times U2 transpose U1 is equal to 0. Okay, so which means that since we have assumed right in the beginning, we are only considering that case where lambdas are distinct. So lambda 1 is not equal to lambda 2. Therefore, U2 transpose U1 equals 0. That means there must be orthogonal. Okay, so for a symmetric matrix, the eigenvectors corresponding to non-distinct to distinct eigenvalues, right, or unequal eigenvalues, they are orthogonal. Now, what happens when eigenvalue has multiplicity m? Okay, this can happen obviously in a symmetric matrix, right? Then what happens is, suppose you have eigenvalue of multiplicity some 5. It is so you'll only have, if you solve it, you'll only get one equation, one eigenvector. But it is possible to construct a system of eigenvectors where they are all orthogonal. They form an orthogonal system of dimension m. Okay, so that's possible, but that's an elaborate procedure. I'll skip that for now. So if you sum this up, we can say that for a real symmetric matrix, right, all the eigenvectors are orthogonal. They form an orthogonal system. So with that piece of information, we can present another theorem, which says that for every symmetric matrix A, there exists an orthogonal matrix Q, such that Q transpose AQ is equal to the diagonal matrix of all the eigenvalues. Okay, so why is that? Let us see that. So let Qi be the eigenvectors of all the matrix. So Qi be the eigenvector of the eigenvalue lambda I. So then if you use the eigenvalue equation, AQI is equal to lambda AQI, then let us define a matrix T, right, which is defined as Dij, where the ijth element of this matrix is defined as Dij is equal to Qij transpose AQI, right. So AQI simply becomes lambda AQI, so you get this. Now lambda I is a scalar, so you can take it out. So you get so lambda I times Qij transpose Qi, and this, since they all form orthogonal matrix, right? So if I and j are, are equal, then it becomes Qi times Qj. And assume they're all unit norm. So then it is equal to 1. It's equal to lambda I, right? Otherwise, it's equal to 0, because if you have two distinct eigenvectors, they're orthogonal, so that becomes 0. So therefore, this matrix D, right, will be such that all the diagonal terms will be the eigenvalues, and outside that you'll all have zeros. Okay, and so you can construct a matrix Q, right, using these eigenvectors, and you can easily show that such a matrix will be orthogonal matrix, because you just multiply that matrix with the transpose of itself, right? You will get a identity matrix. You can easily show that for yourself. So therefore, if you go back to this, right, and you get Q transpose AQ. So basically, I am taking this, writing it in matrix form. Q transpose AQ is equal to D, and therefore you can, if you take Q and Q transpose to the other side, you get A equal to Q into D into Q transpose. And this, since Q is given by, right, as a every column of the columns of the Q matrix are the eigenvectors. So therefore, if you expand this matrix product in terms of the individual elements of D, which are the diagonal terms predominantly, the eigenvalues, and the column vectors of Q, which are the eigenvectors, then you get something like this. So look at this, is a very interesting kind of a decomposition of A, because in this expansion, you are expanding A in terms of n as n terms, sum of n terms, where individual terms consist of a product of the eigenvalue lambda I and the outer product. So note that this is an outer product, right? This is outer product, right, of Qi and Qj. Okay, so this is where we are using outer product, the first example, right? And so this gives you a matrix, and multiply that matrix by the corresponding lambda I, and sum all those terms, and you get the original matrix. Okay, this result is obviously true only for a square matrix, right? And such a decomposition is called Eigen decomposition of A. Just 1 second. Okay, so now that we know how to construct an orthogonal matrix, there's another interesting result that we can introduce. That orthogonal transformation preserves lengths. Orthogonal transformation is nothing but multiplication of a vector by an orthogonal matrix. Okay, so you multiply vector x by q, and then you get a new vector y, and this transformation, which is orthogonal transformation, preserves lengths. That means the length of the input vector will be the same as the length of the output vector. That means it only involves a kind of a rotation. It doesn't change length. Why is that? So take the original transformation, y equal to qx, then take take the transpose, y transpose is equal to x transpose, q transpose. Then multiply these two. You get y transpose y is equal to x transpose q times x. So this is equal to I. Okay, so therefore trivially you get norm y square is equal to norm x square. So length orthogonal transformation is the length preserving transformation. Okay, so that kind of wraps up our simple introduction to eigenvalues and eigenvectors, some of the basic concepts. And also we have only focused on the eigenvalues, eigenvector theory of symmetric matrices. So that's what we'll mostly need in this course, and because the general theory is a lot more complicated and not necessary for this course. Okay, so with this now we're in a position to look at concept of a quadratic form. Okay, so why is it relevant? So because in this course we'll often be looking at multivariate functions. Okay, so we know a univariate function, right? So that is a function that depends only on single variable. Okay, and but in a multivariate function, the function y depends on many variables. And not only that, we'll try to often talk about the maximum and minimum of this function. So we'll try to optimize or find optima of f. F is function of vector where x is in Rn. How to define optima? So how do you define optima for univariate function? So that is straightforward. You have done it in your high school calculus. So if I have a minimum, right, at the minimum the derivative, first derivative is 0. So f prime is 0. And we know that on the left of this point there is the derivative is negative, on the right derivative is positive. So the derivative is increasing from left to right. That means second derivative is positive. Okay, so that means this is a minimum, right? So when the first derivative is 0, second derivative is positive, you have a minimum. And similarly, when the first derivative is 0 and the second derivative is negative, you have a maximum. So this is old story. I've been doing it since your in your childhood practically. But how do you carry these concepts over to multivariate functions? Because if I want to look at a multivariate function, let us say y is a function of just two variables, x1, x2. I don't know, if you want to find a maximum, it might look like a hill, right? And if you want to find a minimum, it might look like a bowl, right? So at the point, at the maximum or the minimum, you can easily guess that there can be multiple derivatives. So because you can differentiate by with respect to each of these variables, you have multiple derivatives. But how do you find out whether it is a minimum or a maximum? What is the equivalent concept of second derivative? Right, because you will have, if it's an n-dimensional vector, you'll have n first derivatives. But what is the equivalent of a second derivative? It won't be n second derivatives. It will be something more complicated than that. It is, if that is the case, then what does it mean to say? Because setting the first derivative equal to 0 is somewhat straightforward to understand. But what does it mean to say that the second derivative is positive or negative? Because if you have lots of second derivatives, what do you mean by what is the equivalent of this inequality? Right? Do we mean to say that all the second derivatives are positive or all the second derivatives are negative? So it gets a bit more complicated in the case of a multivariate function. So to understand that, we start with not the general multivariate function, but simply a quadratic function, because you need a quadratic function even in the univariate case. You need a quadratic function at least to talk about minimum and maximum. If it is straight line, if a linear function, if it is straight line, you can't have minimum and maximum. A quadratic is the minimum that you need. So similarly, even in the case of multivariate functions, you need to study at least a quadratic function to talk about minimum and maximum. And a quadratic function in multivariate case will have this form, can be very compactly represented in matrix notation by this expression. So X transpose AX, where A is a square matrix, and actually A is a square symmetric matrix. We'll see very soon why it has to be a symmetric matrix. And so this expression is called a quadratic form. Let us look at that. So for a multivariate function, the first derivative is a gradient, which we already kind of guessed, because when we have so f is multivariate function dependent on many variables, n variables. So del f is defined as, with respect to x, is defined as dou f by dou x1, etc., etc., dou f by dou xn. Okay, so this is called the gradient and denoted by del with the subscript x, which defines what is the independent variable. When it comes to second derivative, since second derivative is a derivative of the first derivative, right, and each of these functions, that if f is a function of n variables, each of these functions is also a function of n variables. Sorry, no place here, but so therefore, when the second derivative is defined as the derivative of the first derivative, then you have to actually differentiate each of these functions with all its component variables. So therefore, you get a matrix of second derivatives. So second derivative, so in multivariate function, the first derivative is a vector which has n components. The second derivative is a matrix which has n square components because it involves the first derivatives of each of these functions. So if I take first derivative, second derivative of this, then the ijth element of that matrix will be obviously, so it will be like I take any of these first derivatives, like dou fi by, sorry, dou f, sorry, by dou xi. And if I want to differentiate this again with respect to another variable, dou by dou x j, or okay, I'll take this as j and this as I, then that will give me an expression like this. Dou square f by dou xi dou xj. So this is the ijth element of this second derivative matrix, and this matrix is called Hessian. Okay, so denoted by H. So second, yeah, so it's called Hessian, denoted by H. Now we need the concept of. So how do you find a minimum, whether the matrix is whether the function is a minimum or a maximum? So let us look at that. So first, let us take a general multivariate function f, and let us examine if it has a minimum or a maximum at a given point x0. So for that, let us. So what do we do in case of multivariate function, univariate function? You can just expand it out as a Taylor series, and then see what happens around that point. Because if I have a function like this, right, and I am asking if at this point if it is a minimum or a maximum, right, and then I can expand out at this point, and then what I expect is the first derivative should be equal to 0, second derivative should be positive, and so on and so forth. So let us see this, try the same thing here. Okay, so if I expand this out, I get f of x0 plus H transpose G. This H is this perturbation vector, the small incremental perturbation. H transpose G is the gradient, so which we have just defined here. Now the quadratic term in this expansion will turn out to be something like this. H transpose capital H times small capital H is Hessian. H is the perturbation vector, so it will be H transpose capital H times small h, and 1 by 2 factor. It is very similar to the Taylor series of univariate function, but only thing is it's written in matrix notation. Now then you have higher order terms involving cubic terms, and to express them you need tensors, so which is way outside the scope of this course. So I'll just take consider only up to the quadratic term, and I'll just call all this hot. Okay, the higher order terms. So we definitely know that if it is a minimum or a maximum, the gradient has to be 0. So G is 0, so we ignore this term. Okay, then we have the arrow terms are also not necessary to find out if it is a minimum or a maximum, so we'll ignore them. So what we are, and then we have the f of x naught term, which is a constant. So now the constant term doesn't matter because whether this function is right at the origin level, at the ground level, or way up above, it doesn't matter because if it is minimum, it still be a minimum. The constant addition doesn't matter, so we'll ignore that also. So finally, we have concluded that to find out if x has a minimum or a maximum at x naught, it's enough if we understand this function. So if I can find out if this function has a minimum at x naught, that means when h is equal to 0, then the original function will have a minimum at x naught. Okay, so how do you find that out? So we need to first understand what is the shape of this function, right? Around, so what is its shape around h equal to 0, right? So that's a slightly interesting question. It takes a little bit of time, so let us go deeper into this in the next class, right? And that will give us an idea of how to determine whether a multivariate function has a minimum or a maximum at a given point. Okay, so let us stop there. Any questions?